Okay, we are back with another theory of the coordination complexes. One of the earlier theories that was proposed to explain the bonding basically in the coordination complex. We know that the coordination complexes we have a bond between a metal and a ligand. So what type of bond is this? What's the nature of this bond? Whether it's a covalent, whether it is ionic or whatever. So now to understand that nature of this bonding between metal and the ligand, which are the two important components in a coordination complex. In order to understand that nature of that bonding, so the valence bond theory was proposed. It's VBT called. Now, अब सीधे जाते हैं basics पे. तो as per valence bond theory, this bond between metal and the ligand, it's basically a coordinate bond. When you say coordinate bond, that means there is some one component is basically donating. So the ligand is basically donating the electron pair towards the central metal line. When it is donating, so we say this is, and it is donating it through the overlap of orbitals. That means, so this donation occurs between the orbitals on the metal and we have the orbitals on the ligand. The ligand orbitals, they overlap with the metal orbitals which are vacant. Ligand orbitals are filled. So once they are filled, now they can donate it easily. So that's why these bonds, since there occurs overlap of orbitals, this is basically a covalent bond, covalent coordinate bond. So as per the valence bond theory, the nature of the bond between the metal and ligand is basically it's a covalent bond, but rather it is a covalent coordinate bond where the orbitals, atomic orbitals on the central metal line, they are vacant. They overlap with the filled orbital on the ligand. Hence it donates, once it overlaps, the ligand donates the lone pair into the vacant orbital of metal. Now when we say that it's a covalent bond, that means now the concept of hybridization comes into account. So that means we have the concept of hybridization in the valence bond theory. Hybridization. Hybridization we know is basically the mixing of atomic orbitals prior to the overlap. So now to understand this, let us go to the complex. We have a complex Ml6. That means we have a central metal line here. Any atom, any metal from the transition series, whether it is 3D, 4D, 5D, whatever. So we have 6 ligands here. That means we have 6 type of Ml6 bonds. Fine. So when that means now the metal has to make available 6 vacant orbitals, and then they should overlap with the 6 orbitals, ligand orbitals. And during when they overlap, then these ligand orbitals, they will donate their lone pair into the vacant orbital of the metal. Now that means metal will make available, the metal will make available appropriate number of vacant orbitals. So prior to the overlap. Now when it made available the appropriate number of orbitals, and then those orbitals, they undergo the hybridization, or they undergo mixing, or they undergo the process of hybridization. So the result of this hybridization is that now we have available 6 orbitals, which are 6 metal orbitals, which are all same energy. So they are of same energy. This is the concept of hybridization. So once we have 6 orbitals available on the metal of the same energy, then those 6 orbitals, they will overlap with the 6 ligand orbitals. 6 ligand orbitals. And then we have the 6 coordinate bonds in Ml6 type complexes. Same is the case, we have 4 coordinate bonds in the Ml4 type complex. Fine. Now this is the basics of the valence bond theory. Now this is it's just simply based upon the hybridization and the overlap process between the ligands and the metal line, where the metal line receives the lone pair from the ligand, and hence there's a coordinate bond covalent coordinate bond formed. Fine. Now, this is the important thing. Let's move to point number 2, basics. Point number 2 इसमें ये होता है. Now we have again, we have this 6 coordinate complex. So we have Ml6. So it has to make, metal ion has to make available 6 orbitals. So we know jo valence, if you take the example of 3D series, 3D transition series, let us take the example. 3D transition series में जो last जो electronic configuration होता है, let us have the example of a compound iron in order to understand this. Let's take the example of a compound FeCN whole 6 iron hexacyanoferrate 3 negative. So it's, if you see the atomic number of iron, that is 26. Now the oxidation state is +3. So your oxidation state is +3. So that makes the Z now 23. So if we write the electronic configuration of Z +3, so that will be, we have, if now मैं end वाले orbital जहाँ लिख रहा हूँ जहाँ important है, we have in the end 3D, 4s, 4p and 4d orbitals. So 3D we have available in the 3D orbitals 5 electrons. ठीक है ना? आप इसमें से निकाल लीजिए 3, तो you will get 5 electrons here. So this will be 0 and that will be 0. ठीक हो गया? So we have 0 here, 0 here. Now हमें चाहिए 6 orbitals. So what the central metal ion will do here, it will make available, the central metal ion will do is that these are 5d orbitals. One, 2, 3, 4 and 5. Take. So as per valence bond theory, now you need how many orbitals? 6 orbitals. So obviously we have 1 from S, 3 from P, so that makes us 4, so we need 2. As per this theory, we have the pairing here takes place. So we have these 2 electrons will get paired here. So we have now new condition, which is gets paired here, 1 remains here, so nothing is here. So we have now these 2 orbitals, they are from 3D, and then we have 4p available here, which is vacant, and then we have 4d available here, 4d. Now we need 6 orbitals, so that is 1, 2, 3. Sorry, we have 4p here. Sorry, it is a 4p first. 4p. So we have 4p here. So we have 4p here. It's 4s. It's 4p. So that makes that 2, 3, 4, 5, 6. So it is this available and this available. So overall, the hybridization is D2, S and P3. So these are 6 orbitals. So as per valence bond theory, the hybridization is D2sp3 in this complex. So it is these 6 orbitals where the ligands donate the electron pair, 6 ligands. So it receives the electron pair through 6 coordinate bonds from the these 6 ligands, which is cyanide in this case. Fine. So that means turns out that the hybridization is D to sp3. Now since the inner d orbital rather than the outer d has, so outer d was here. So I have not shown here, outer d was here. That is 4d. Since the inner d has participated in the bonding, this type of complex, it's called as an inner orbital complex. Inner orbital complex. Now, अगर आप यहाँ थोड़ा गौर करें तो it was यहाँ पे originally there were 5 unpaired electrons. Now the pairing has got reduced, so it's called as a low spin complex. क्योंकि जो unpaired spins थी they got decreased. ठीक, spin value got decreased, so it's a low spin complex. So as per valence bond theory, there's a concept of inner orbital complex and low spin complex when we have a case like cyanide. And as per valence bond theory, when you ask the valence bond theory why it takes this inner D takes participate in the bonding rather than the outer D, why the pairing takes place, so the answer is that this is a strong ligand. So it's a strong ligand. Just the answer is a strong ligand. But the things are not clear how. Number one. Fine. So likely we'll take one more example of 6 coordinate complex now to completely visualize the valence bond theory. Now let us take another example. I believe this will be enough information as far as the valence bond theory at this level is concerned. Now let's take one more example of valence bond theory. The cobalt hexafluoride. Cobalt, so we have another example of Ml6 cobalt hexafluoride, 3 negative. So the Z, now that oxidation state यहाँ पे cobalt का +3 है. So if we take its original Z atomic number, so that is actually 27. So that turns out that Z plus 3 is equivalent 24. तो इसका अगर हम electronic configuration write करें, so we'll end up with 3Ds. 3D is that we have 3D, we have 4S, so we have 4P and we have 4D. Now in case of 3D, we have a total of 4, a total of 7 electrons. Fine. We have total of 6 electrons because you got 24. 6 electrons. And here we have 0. Remember I am talking about this one which is actually present there. So 3D is 6, 4 is 0 and 4 P0 and 4D0. Take. Now we need 6 orbitals available here. So that means we make 5D orbitals because D has 5 orbitals. So originally it was like this, 3, 4, 5, 1, 2, 3, 4, 5, it was like this. Now in the complex now, in order to explain the bonding, valence bond theory says that this electron is basically valence bond theory says that this electron, if you pair it also, it says that this participates in the bonding, this participates, and then the 3 from here they participate in the bonding. So we have 1 orbital of S, 3 of P, and this is makes it 4, 5 and 6, so 2 from D. So the valence bond theory doesn't gets things, it says that it doesn't pairs here. Okay, so that means you have S, P3 and D2. Now I am writing D2 rather than D2sp3 because now this is called as the outer, since the outer d orbitals are participating in the bonding. So we say it's an outer orbital complex. Outer orbital complex. ठीक. Now अब देखिए यहाँ पे क्योंकि ये पेयर नहीं है, that means now we have maximum number of spins available. So the spin value is increasing now. So its spin is very, very high. That means it's called as a high spin complex. High spin complex. So as per valence bond theory, now this type of compound, we have an outer orbital complex, high spin complex. When you ask valence bond theory why this ligand, when the previous complex also was similar type, why we have this ligand, this fluoride, it doesn't makes these electrons get paired. The answer says that fluoride is a weak ligand. When you say what do you mean by weak ligand, so the things are not clear. So the concept of, so valence bond theory, it tries to understand the hybridization and the formation of complex with the help of the overlap, but then it doesn't explain the concept of the strong ligands and the concept of the weak ligands. Now, अगर आप यहाँ देखिए, यहाँ क्योंकि आपके पास 1 2 3 4 5 इलेक्ट्रॉन्स हैं, valence bond theory says now this complex it has magnetic moment, because जब आपके पास electrons होंगे which are unpaired, so we know that the electrons, they are not at rest, so their movement creates the magnetic field. Since you have more pairs in the parallel direction, so the magnetic vectors are getting added up, so it has a larger magnetic field. So it says that the magnetic moment is given by n into n plus 2 Bohr magneton. Fine. So where n is the number of unpaired electrons. अगर आप previous complex आपके mind में था, in the previous complex where the electrons got added up, तो previous case में when the electrons got added up, वहाँ पर सिर्फ it was only 1. So in the Fe, C and 6 whole 3 complex, we were having only 1 unpaired electron. In this case, cobalt hexafluoride complex, we have 4 unpaired electrons. So we have larger magnetic moment here as per this formula. Take Bohr magneton. While as we have less magnetic moment in this complex as per this formula. So the magnetic moment is given by, even though ये जो value यहाँ पे propose, ये जो equation propose यहाँ पे कर रहा है कि valence bond theory, sometimes it gets closer to the experimental value, but then it is always not the case. क्यों ऐसा नहीं होता था? Because magnetic moment में हम जानते हैं कि orbital motion का भी concept होता है. So it straight away takes away the orbital contribution of orbital motion to the magnetic moment. So it only relies on the spin value of the complex. So sometimes it matches, theoretical and experimental does match, but sometimes there's ambiguity. So it again says nothing about the why there's ambiguity in the complex. So overall, to some extent, the valence bond theory could explain the bonding in these complexes, but then there are many shortcomings. Now let us go to the shortcomings of this. So some of the basic shortcomings of valence bond theory. So the drawbacks of valence bond theory. Drawbacks of valence bond theory. Number 1, first one जो है, it couldn't explain the magnetic property of complexes properly. So the magnetic property of complexes was not understood completely. It was partial. Second, हमने कहा कि ये जो we have observed many times that these in the lab that metal ligand complexes, they are very much colored, or sometimes absorption spectra 500, 600, 700 के आसपास भी जाता है. So as per valence bond theory, it stays neutral here. Stays neutral means couldn't explain the optical properties or optical properties. Could not explain the optical properties of metal ligand complexes. Third main shortcoming जो था इसमें, stability of the complex. क्योंकि metal ligand complexes sometimes stable भी हो जाते हैं, sometimes highly stable रहते हैं, sometimes you keep them under the environmental conditions or even room temperature, they are getting degraded. So the stability was not explained. One more was that, जैसे मैंने अभी कहा कि why there are some ligands are weak, concept of weak and strong ligands was not clear. Strong ligands was not clear. It was not clear. और एक point जो इसका shortcoming था, जिसे मैंने कहा था that if you have a 6 coordinate complex, as per valence bond theory, it is always an octahedral complex. The geometry is octahedral. Now likely if you have a tetra coordinated complex, as per valence bond theory, the geometry can either be tetrahedral or square planar. यहाँ मैं designate कर रहा हूँ इनको by point groups. So this is basically square planar, and this is tetrahedral point group. This is octahedral point group. Now, when you ask why some complexes are tetrahedral, why some complexes, their geometry is octahedral? The answer is we don't know. So it couldn't actually, so it could not explain the existence of tetrahedral and octahedral, sorry, tetrahedral and square planar complexes, T4H. The why 4 coordinate complexes, that some complexes are tetrahedral and some you are designating square planar, why they are forming, it could not explain them. So overall, valence bond theory relies on that the bond between the metal and ligand is a covalent bond, it's a covalent coordinate bond. It relies on the hybridization concept and the overlap of metal ligand orbitals, and it relays, it's basically, it tries to understand many properties but in a qualitative manner. So it basically explains many things to some extent, but then it is a qualitative one. So this is all about the valence bond theory. I believe this, I've tried to make it concise and as much as proper, as much as possible. So in case of any question or confusion, you can please write me here, makandchem@gmail. So this is your c@gmail.com. Or you can write down the comments. I will be happy to answer. This is all for the day.